Hello, this is a video on Oneway ANOVA. ANOVA is analysis of variance. There are three assumptions of a ANOVA procedure. One is that scores in each population are normally distributed. Another one is that each population of scores has the same variance, also called homogeneity of variance. And the third assumption is that the observations are all independent. So in other words, knowing something about one observation does not tell you anything about any of the other observations. So ANOVA is a procedure that you use when you're comparing more than two means. T-test was when you're comparing two means, and ANOVA is when you compare more than two. It could be 3 means, 4, 5, 6. You could compare 3 different age groups, for instance, on some dependent variable. And the dependent variable is at least interval level or ratio level data, continuously measured data. So I'm going to go over just a few steps that you had to go through to calculate all of the estimates in the ANOVA procedure. Oneway means that you only have one independent variable. In this case, we just have 3 groups. So group membership is the independent variable, and all of these measures, there are 9 actual measures, and they're all measures on your dependent variable. And we're going to try to explain some of the variance of the dependent variable with our independent variable. So the grand mean is one of the first things that you have to calculate, and it's the mean of all the values in all groups. So if you added up all of these 9 numbers, you would get 99. And so if you divided it by 9, you would find a grand mean of 11. The next thing is sum of squares total. And it's the sum of all the squared deviation scores from the grand mean. So this is a lot like calculating the variance. This is the total sum of squares, which means really the total sum of squared deviations. So this here in yellow is how you calculate sum of squares total sum of squares. And as I say, for each of these numbers, you get the squared deviation scores from the grand mean. So 6 minus 11 squared is this. 4 minus 11 squared plus 14 minus 11 squared plus 7 minus 11 squared all the way through the whole data set. So if you had 500 numbers or 500 people in your data, you would add up 500 squared deviation scores from the grand mean. In red here, I'm adding all of them up. 6 minus 11 is 5, and squared is 25. So you do that for all of these, and you add them all up, and you end up getting total sum of squares of 204. So that's the first thing we calculate. We will need to remember this 204 for the total sum of squares. Okay, so the next thing that we calculate is the sum of squares group. And sum of squares group tells us how much variance in the dependent variable can be explained by group membership. Okay, so in red here is how we calculate sum of squares group in the Oneway ANOVA. And instead of taking the square deviation scores from every individual score from the grand mean, we take the square deviation scores of the mean of each group and add them all up. Here's the formula. Forget this n for right now. It's the sum of the mean of each group minus grand mean squared. So the first one is 8 minus 11 squared, and that's right here. And then the second one is 10.33 minus 11 squared. And the third one is 14.67 minus 11 squared. And this n right here is what you multiply all of these square deviation scores by. It happens to be how many numbers make up the means that we're subtracting from the grand mean. So we have 3 here that make up this 8. and 3 that make up this 10.33. So that's what we have here, 3 times all of this. So you do what's in parentheses first. 8 minus 11 is 3, minus 3, squared is 9 right here. 10.33 minus 11 squared is 0.44. 14.67 minus 11 squared is 13.44. So that'll be 3 times, you add all these up and you get 22.89. So 3 times 22.89 equals 68.67. That's our second number that we'll use to build what's called a summary table. The summary table looks like this. It summarizes all your sum of squares. We can subtract from 204, 68.67 to get our sum of squares within our sum of squares error. And we already said that this is 8 degrees of freedom because we have sample size of 9 minus 1 is 8. And this is 2 degrees of freedom because we had 3 groups minus 1 is 2. And this is 6 because that's how much is left over. So now to get mean square, we divide 68.67 divided by 2, and we get 34.33. And we divide 135.33 by 6, and we get 22.56 or 556. And now we take the ratio of 34.33 divided by 22.16, and we get 1.522. Okay, and just like before, we find our critical value for this F ratio. And let's look at the F table. And the way we do this is, remember we had 2 degrees of freedom for our numerator, which was between groups, and we had 6 degrees of freedom for our denominator. So here's the degrees of freedom for numerator and degrees of freedom for denominator here. So we had 2 and 6. So you go where these two intersect, and we get a F critical value of 5.14. And as this shows, the F distribution doesn't really look like a normal distribution, of course, because it's a different distribution. It typically tapers out a lot. It's really like a one-tailed distribution that goes to the right. And our critical value is 5.14. And our F is like 1.522. This means we do not reject the null hypothesis, because the null hypothesis is that there's no difference between the groups. In this case, we would say the null is first mean equals second mean equals third mean. Of course, this could be more means in ANOVA if you had more means you're comparing. And the alternative hypothesis is that at least one of these pairs are not equal. So what we're testing with this 1.522 F ratio is called the omnibus test. And the omnibus test is just testing to see if at least one pair of these means are not equal. So you have to actually go a little bit further with the ANOVA after you have this original omnibus test that we're testing here. You have to see which pair or pairs are different. And that's when you start doing some post hoc analyses and do things like what's called multiple comparison techniques, which are techniques for making comparisons between 2 or more group means after you have found a significant F ratio.